Robin on exponential separations between shallow quantum and classical circuits.
Thanks for the introduction, and thanks for having me here. I'm going to be talking about exponential separations between shallow quantum circuits and shallow classical circuits. And this is joint work with Adam Benny-Watts, Luke Schaefer, and Avishai Tal. Okay, to motivate the setting, we're looking for provable separations in power between quantum and classical computers. So that's the big picture idea. So we want examples of problems that there's an exponential gap between quantum and classical, and that you can prove this. So for example, things like factoring. We do believe that factoring can be solved in polynomial time on quantum computers, and that maybe we know. We believe that it can't be solved in polynomial time on classical computers, but we can't prove that, and because it would be a huge breakthrough in complexity theory if you could prove something like that. So if you want to focus on provable statements or provable separations, you could do stuff in query complexity, for example, or communication complexity. These are other avenues you can prove something. But the context of this talk is we're going to talk about circuits, and specifically about constant depth circuits. So this is a model of computation where we can actually prove unconditional results. And that's one of the motivations why we study constant depth or shallow circuits. The other motivation might be just that shallow quantum circuits might be implementable on near-term or medium-term quantum computers in the future. So I'll give some practical motivation for looking at shallow classical circuits. Okay, and so the players in this game are constant depth circuit classes. And if you haven't seen these before, let me introduce them to you. And let me start with the classical shallow circuits class that's called NC0. So some of you might know what this is. It's constant depth. So what constant depth means, the depth does not depend on the input size. So that's what constant means. Polynomial size. So everything we're going to talk about today is polynomial size circuits. Classical circuits. And the gate set is important. And the gate set is, you just have these gates, which is you have AND gates, which take in 2 inputs and output 1 bit, OR gates, which take in 2 bits, output 1 bit, and negation gates. I mean, it turns out that for NC0, it's not really relevant what the gate set is. Any reasonable constant size gate set would do, but conventionally, this is the set of gates that we assume. So this is NC0, set of all classical circuits of constant depth, polynomial size, use this kind of gates, and I'll just give you an example. Maybe your input bits are x1 to xn, and you have some gates like this, I don't know, OR gates, AND gates, and there's more of them, whatever, something. And you might have multiple output wires, which I might call y1, y2, y3, whatever, ym. So throughout this talk, I'm going to assume that our circuits have n inputs and multiple outputs. So it's not just computing Boolean functions of one output, but there's many output bits. This is the first player that we're going to be introduced to, NC0. And feel free to ask questions at any point. Yeah, okay. No questions so far, right? The other player, maybe I'll introduce it here. AC0 is very similar to NC0, except the gate set is different. And the gate set, so all of this is the same. But the gate set is the same gates, but now they can have unbounded fan-in, which means they can take in as many inputs as they want. And it's kind of clear how the AND and OR gates would generalize to unbounded fan-in. So if you don't know what these functions are, the AND function is where the output is 1 if and only if all of its input bits are 1. The OR function is 1 if and only if any of its input bits is 1. Right, so this is AC0, constant depth, polynomial size, classical circuits, where you have unbounded fan-in AND and OR gates. Everyone's on board so far? Okay, so these are the only 2 classical complexity classes that you need to know about for this talk. And finally, we're going to talk about the quantum analog of this class over here, which I'm going to call quantum NC0. So this is, as the name suggests, a quantum this thing. So the only thing here that you have to generalize, so constant depth, polynomial size, all that stuff is the same. The thing you have to generalize is the gate set. And for concreteness, I'm just going to, so I'm saying quantum, everything else stays the same. And for concreteness, I'm going to take the gate set of Hadamard T C naught. I don't know. Choose your favorite gate set. I guess it doesn't matter. Let's throw something else in. Let's throw in phase, whatever. Just choose some complete gate set, or Clifford's plus T, maybe. Maybe that's a more convenient gate set. Doesn't matter. Some gate set of 2-qubit gates. Some discrete set, ideally, like something that has, like, let's say, size 5 or 6 gates. And essentially the same definition, and maybe let me just draw a little picture just to give you some intuition for what this might look like. Now your inputs are qubits, and then you have some gates, possibly 2-qubit gates and 1-qubit gates and so on. And at the end of the day, you might have output bits y1 to yn. And that's what I'm going to call a constant depth quantum circuit, or QNC0. Any questions about this so far?
In this case, it's actually going to be a linear number of gates instead of polynomial.
That's right. Yeah. So I'm also going to allow polynomial number of n syllabits. So I guess you could get more. Yeah, but it doesn't actually matter. It seems like you generally always need linear number of. I think everybody's on board. Yeah.
Assumptions of initial state in this model?
No. So what I'm going to do is I'm going to look at circuits solving problems. So the initial state is going to be the input to the problem. So more precisely, I'm going to look at relation problems or search problems. And what these problems are is you have some set of inputs. Or maybe let me step back a bit. Before relation and search problems, the normal thing that we usually look at is function computation problems, where you have some input, and the input uniquely corresponds to one output, like it's a function in the usual sense of the word function. So you have some, let's say this is the input domain, and this is the output domain. You have some input here, and the input gets mapped to one guy over here. A relation problem is where each input may have many outputs. So that's what a relation problem is. And we're only going to talk about relation problems right now. And it turns out this is essential because if you look at function computation problems, QNC0 and NC0 turn out to have the same power, so it's not very interesting. So for relation problems, what's going to happen is the input, x1 to xn, is going to be some input here, and the output will be the thing you output over there. And maybe the thing I should mention, which is what spurred all of this work, is a very nice result of Bravi, Gossett, and Koenig from 2018, which showed that there is a relation problem, let me just call it R, that can be solved by a constant depth quantum circuit, QNC0, but R is not in NC0. So you can solve it with the quantum circuit of constant depth, but you cannot solve it with the classical circuit of constant depth. So we've taken two models of computation that are analogs of each other, so it's like an apples to apples comparison. And we've shown that the quantum model is more powerful, unconditionally, no assumptions. Or rather, Bravi, Gossett, and Koenig showed this. Okay, so that's great. This is the kind of thing we like doing in quantum computing, right? Showing separations between quantum and classical models. So this was Bravi, Gossett, Koenig 18. And the work I'm going to tell you about today is a strengthening of this work, a follow-up of this work. So our work. So what we do is we extend the lower bound further to a more powerful classical model, so to AC0 circuits. So AC0 circuits are extremely well studied in classical complexity theory. In fact, have been since like the early 80s. Super interesting model of computation. You can say a lot of things about it. We understand it very well. And they're also a reasonably powerful model of computation. In fact, they can do many surprising things that you wouldn't expect that AC0 circuits can do, like they can add numbers and so on. And you might think that to add two n-bit numbers, you would need depth that depends on the number, but in fact, it doesn't. Also, AC0 can do some trivial things, like computing the AND of all n bits, all n input bits, obviously, because that's just a gate. But NC0 can't do that. So NC0 is a very weak class, whereas AC0 is a reasonably powerful class. So that was one of the motivations of our work, is just extend this lower bound to AC0 circuits. And our first result is just that this problem is not in AC0. And this is what I'll say a little bit about today. But we have some strengthenings of this as well. So in fact, we can show this problem is not even in AC0 with essentially with sub-exponential size circuits, or even close to exponential size circuits. So not only can polynomial size constant depth circuits not solve this, but not even exponential size circuits can't do it. And the technical statement is something like, if it has depth d, then it's not in AC0 with size exponential in n to the 1 over 10d, something like this. So if you fix a depth, let's say depth 10, then even an AC0 circuit of size exponential in n to the 0.01 can't solve this problem. And then we further extend this to an average case lower bound, which means that we show that Essentially, if you pick a random input, then the probability that any AC0 circuit can solve this is also exponentially small. So notice that you can always solve any problem on, like, let's say one input. Or there's 2 to the n possible inputs. You can always solve any problem on one input by just having a circuit that hard codes the answer to that one input. So saying that you can only solve it on an exponentially small fraction of inputs is a very strong statement. That's kind of the best you can hope for. So we can also prove that. I won't actually get into that, so maybe I won't write that here. Okay, so that's the statement of the result. Any questions about that? No, we're all happy with this? Okay, so I want to tell you a little bit about the problem that's used in this work, because I think the problem's kind of cute and it's easy to understand. And it's also, it's easy to see how we came upon the problem. Rather, I'm going to tell you the story of how we found this problem, which is also one of the motivations of this work. Really, the problem used in the original separation is more complicated, at least in my opinion. And it's a little harder to see why that problem was chosen. Whereas in our work, I think the problem is really intuitive. Or at least I hope to convince you that that's the case. Okay. No questions so far about this? All right, good. So the problem is it's not exactly the following, but it's going to be a small variation of the following problem. And this problem is what we call the parity halving problem. And it has been studied before under various names like the n-party Mermin game, and it's actually a generalization of the GHC problem, but let me just call it this because you'll see why. So the parity halving problem, PHP sub n, you have some input, which is an n-bit string, with the promise that the Hamming weight of x is 0 mod 2. So the number of ones in x is even. That's the promise. And your output, so recall this is not a function computation problem. There's not a unique output. There's many valid outputs. So your output is just any, there should be n. So the input is of size n. And your output is any string of length n such that, now there's a condition on y. And the condition, let me write it out explicitly. It's just, as a formula, the function is just that y should be congruent to x divided by 2 mod 2. But let me spell this out. What this means is that so x is a string whose Hamming weight is even, right? So if you're an even number, there's 2 possibilities. You're either 0 mod 4 or 2 mod 4. So if x is 0 mod 4 and 2 mod 4, these are the only 2 possibilities. What we want, in this case, your output should be 0 mod 2. And in this case, it should be 1 mod 2. So your task as the person solving the problem is to accept an input string whose Hamming weight is even, and then output a string which is even if the input string's parity was Hamming weight was divisible by 4, and odd if it was divisible by not divisible by 4, and it was 2 mod 4. That's the problem you're starting with. Is that good? The problem makes sense to everyone? Okay. And it turns out that this problem is actually pretty straightforward to solve with a QNC0 circuit if you allow me to start with a cat state. So for those of you who don't know what a cat state is, this is what I'm going to call the cat state. So cat on n qubits is just this state, all zeros plus all ones. So if the QNC0 circuit, in addition to its actual input, is also allowed to start with a cat state, like this just like falls out of the sky, where, it's not being prepared by our constant depth circuit. We just have it as a resource. Then it's actually really easy to solve this problem. And this is just a generalization of the 3-player GHC game, if you've seen this before. And the idea is just you have n qubits in the cat state, and you have your n input qubits, the x1 to xn. Each of them is going to apply a controlled phase gate on its corresponding qubit in the cat state. So the first input qubit is going to apply a control phase gate on the first qubit of the cat state, the second on the second, third on the third, and so on. So these can be done in parallel, so it's going to be a depth 1 circuit. And what that's going to do is every time your input bit is 1, it's going to add an I over here. Right? That's what a controlled phase would do. And because there's going to be a bunch of x's that are 1. In fact, how many x's are going to be 1? Exactly the Hamming weight of x. The state you're going to get is 0 to the n plus I to the Hamming weight of x, 1 to the n. So that's not very surprising. This is a depth 1 circuit so far. And we know that x is, or Hamming weight of x is even, right? That was part of our condition. So in fact, this splits up nicely in these 2 cases. If x is 0 mod 4, then here you get back the cat state. So 0 to the n plus 1 to the n. Right, because if this is 4, I to the 4 is 1. And in the other case, you get 0 to the n minus 1 to the n. Okay, so your quantum circuit has prepared one of two states, depending on the two cases that we're trying to distinguish in the input. So that's great, right? We've already, in some sense, distinguished the two cases we're trying to distinguish, except these are some quantum states. What do you do with them? The first thing you observe is that they're orthogonal. Take their inner product at 0. So this is great. This means we're outputting two orthogonal states. But we had some other condition that we were supposed to output a string of length n. And it so turns out that if you just apply the Hadamard gate to this on all n qubits, Hadamard, same thing here, you will get exactly a uniform superposition over strings that satisfy this criteria. So over here, if you apply the Hadamard superposition, you will get all strings whose Hamming weight is even. And to this state, if you apply the Hadamard gate, or n Hadamard gates, you'll get a superposition over all strings whose Hamming weight is odd. And so that's it. That's the circuit. And then you measure it, output this. And now your QNC0 circuit with a cat state has solved this problem. Does that make sense to everyone? So this, we say in our paper that PHPN is contained in QNC0, except it's not contained in QNC0 because it needs this cat state. So the complexity theorists will often use this notation to mean that the circuit class is given some extra advice state, some state that doesn't depend on the input, just like the cat state. The cat state had no relationship with the input x, right? It's just some advice. It's some extra resource that the circuit is given, and we say QNC0 slash cat, or in the paper, actually, we write QNC0 slash, and then there's a picture of a cat, which is kind of hard to do on the board, but something like this. So this is the complexity class that it's in. Okay, so any questions about this so far? No, it's pretty straightforward. And the cool thing is, it's in the quantum class, and the cool but also difficult to prove, somewhat difficult to prove, is that this problem is not in AC0. So that's the in some sense the difficult part of this paper, is proving that it's not in AC0, and in fact proving that it's not in AC0 even if you allow me exponential size, like size n to the 1 over 10d, and even if I only have to succeed on an exponentially small fraction of the inputs, which means even if I only have to succeed on a 1 over x n to the 1 over 10d fraction of the inputs. And maybe I'll say a sentence or two about this, but I want to explain to you how we get rid of this cat state, because so far this is not a solution to the problem we're seeking out. And I guess most of you here are probably more interested in the quantum part, so I'll focus most of the time on that, but I'll say a few sentences about how we prove this. And the way we prove this is in 3 steps. So we start with proving something weaker. So we want to prove it's not an AC0. What's a weaker thing you can prove? You can prove it's not an NC0. Sure, so that's a weaker statement. But what's actually even weaker than proving something is not an NC0. So in NC0, recall that any output bit can depend on some constant number of input bits, because the fan-in is bounded. So every gate can involve two more things, and like as you go down depth d, you can involve, say, 2 to the d things. It's still constant, but you can depend on a bunch of things. An even weaker model would be if y1 could only depend on x1, and y2 could only depend on x2, right? Like this is a kind of silly model. But this has actually been studied. This is an n-party communication game, where you give n inputs to n different players, and you ask them to output some n-bit string that satisfies a certain constraint. This is just an n-party generalization of the GHZ game, if you've seen this before. And it's not so hard to prove that the classical players cannot win the GHZ game, or they can only win it at probability half plus exponentially small, whereas quantum players can win it with probability 1 if they start out by sharing a cat state. So this is an old result. So that was already known. So that gives us the claim that this problem cannot be solved by a very special NC0 circuit where every output only depends on one input. Then we go from there to NC0 circuits, essentially by saying that there's not too many gates, and every output can only depend on a couple of input variables, a constant number of them. So we can essentially just partition the output into some order n number of blocks so that each of those output bits only depends on independent inputs. And then this kind of takes us back to the communication complexity game. We kind of just give all of those independent inputs to player 1 and the next set of independent inputs to player 2 and so on. So we kind of reduce back to this communication complexity setting, which is already known. And that gives us this NC0 lower bound. And finally, to go from AC0 to NC0, this uses some more heavy machinery. From AC0 circuit lower bounds, we use switching lemma, which is a common technique for proving AC0 circuit lower bounds. Except the off-the-shelf lemmas don't work as well because we're really dealing with function problems, relation problems, and not single output problems. And many traditional AC0 circuit lower bound techniques only consider the case where there's only one output variable, and we have to use the fact that there's many output variables. So anyway, there's some work here, but let me not talk about that. Let me get to how do we fix this issue of getting rid of the cat state. So one thing to note, maybe it's not totally obvious, but the cat state cannot be created in QNC0. You just need log depth to create this cat state. So there's no solution that's going to be like, oh, here's a slick algorithm for creating the cat state. That's not going to happen. So what do we do? And yeah, what we do is we can create something that's kind of like the cat state. It's something what we call the poor man's cat state. And this can be done in QNC0. Let me just explain it with an example. So let's say you start out with a line of qubits in the plus state. And for each of these qubits, you measure the parity of adjacent qubits. So you measure whether these two qubits are equal or not. So is this in the state 0, 0, or 1, 1, or not? And I'm going to call this bit D1. So you perform an actual measurement that distinguishes the case where they're the same or they're different. And this last guy, let me call this Dn minus 1. These are some classical bits. Right? These are the measurement outcomes. So let's say you got the measurement outcome where all the Ds are equal to 0. So you got D1 equal to 0, D2 equal to 0, and so on. What does that mean about the resulting state over here? What that means is that this qubit's value is equal to this qubit's value, is equal to this qubit's value, and so on, if all their parity is 0. And the only two states that have that property are 0 to the n and 1 to the n. And if you work it out, you'll see that if you do get the all 0 string, you in fact have created the cat state. And this is a constant depth circuit, right? You started out with all pluses, that's a depth 1 circuit. And then you just measured all of these guys. That can all be done in parallel, or maybe not technically in parallel because these two guys are touching the same qubit, but you can do them in 2 layers or something, whatever. It's a constant depth circuit. And you created the cat state, right? So that's great, right? What's the problem?
What do you mean by conditioning?
Right. What do I mean by conditioning? Right, exactly. So the probability that these are all 0 is extremely unlikely. Right? It's exponentially unlikely. So that's not good. So instead, what you can ask yourself is what happens in general for some arbitrary set of D1 to Dn minus 1. And what happens is you get some superposition like this. Some n-bit string z plus z complement divided by root 2. So in this case, z was all zeros. But this is just some string and its complement divided by root 2. And we call this guy, this state over here, the poor man's cat state. Because it's kind of like a cat state, but it's not, right? OK, and so how do we fix the problem? So, and this state is creatable in QNC0, as I described. It's just that this z is not in your control. It's a completely random string z and z bar. But you can derive the value of z because you have these measurement outcomes. So you can figure out what z is from these things, right? Because there's only 2 strings that will satisfy this. There's n variables, like z1 to zn, and there's n minus 1 constraints given by these parity constraints. So there's 2 strings, and you can figure them out. It's something like there's 2 possibilities for this guy. This guy can be 0 or 1. But once you fix this guy, let's say he's 0, then this has to be D1, this one has to be D1 XOR D2, this one has to be D1 XOR D2 XOR D3, and so on. So once you have the Ds, you can figure out what Z and Z bar are. Yeah, you have a question?
What's the complexity of that?
Yeah, that's very complicated. So I'm just saying in principle you can figure it out. Yeah, you certainly cannot figure it out in constant depth because you're computing parities of very long strings. But the Ds encode the Zs in a complicated way. OK, so we have this poor man's cat state that we can prepare in constant depth. We have this parity having problem, which needs a cat state to solve it. So what are we going to do, right? We're going to do this classic life gives you lemons, make lemonade strategy, which is just use this state instead and see what happens. Right? You'll get some quantum circuit. So the quantum circuit is just create this poor man's cat state, and then just run the circuit, assuming it was a cat state, and something happens. The quantum circuit will do something, and that's the computational problem. So that's it. So just go with what happened. Like you're like, okay, I couldn't do it. Well, I'll just take the closest thing I can do, plug that in. You'll get some computational problem. What is the problem you get? I can say what it is. It's actually not very complicated. It's just here you get an extra term. You get a plus x inner product z. That's what's going to happen. Like the output will satisfy the following condition, that the Hamming weight of the output string y will be x divided by 2 plus the inner product of x and z. X and z are both n-bit strings. So this inner product is just sum over I x I z I. OK, so that's something. The other thing that you can also output is you have these bits lying around, right? So you also output those. Because otherwise, z is not defined. Like if the input is x, you output some string y, And if it has to only satisfy this equation for any z you choose, then you can just choose z to be, this is always satisfied for some z. So you have to somehow output z, except you don't know how to output z because you don't have z. You just have this poor man's cat state, which is going to get destroyed by your algorithm. But you have this string, which encodes z's. So the new problem is going to have two outputs now, which is not just y, but it's going to have y and this string d, the thing you measured. And the new output criterion is this one. And that's our problem. So that's a problem that is now in QNC0 without this cat state by construction. Like that's how we came up with the problem. And it's also not in AC0. This takes a little bit of work to prove. And actually, I glossed over one detail, which is that this poor man's cat state, there's actually many different ways to create it. Like this was just one idea, that you take a line and measure all the neighboring qubits. But the other thing you could do is you could take a grid and put qubits on the grid. And do the same thing. Just make all the measurements of all the pairs, of all the neighbors. And you'll again get some string of parities, D1, D2, and so on. Again, if all of them are 0, then this is the cat state. If they're not 0, then there's something. It turns out this is the one that we actually need to use. This construction doesn't work, but that's just a minor detail. It's the same story, essentially. We were able to make some kind of cat state, which was not really the cat state we wanted, but we just plugged it in. We got a problem, and it remained hard. And we really prove it by deduction. So this new problem, the one where we have this poor man's cat state, we call it the relaxed parity halving problem. And we show this is not an AC0, but it's actually an implication this way. So all the work we did in proving this was not an AC0 was actually useful. It follows from that this problem is not an AC0. And in fact, all the lower bounds we show, like in fact, all these size, depth, trade-offs, et cetera, that exponential size AC0 circuits cannot solve the problem in exponential small fraction of the inputs. Whatever we prove about this original problem, we can just get it directly for this problem. So from the perspective of AC0, these problems are basically the same. Like their hardness is the same. Except from the perspective of QNC0, they're completely different because this problem can be solved by QNC0 circuits. The other one could not have, or we didn't have cat states in QNC0, we couldn't solve it. So that's the story of this problem that proves this result. And maybe the final thing I just wanted to say about the problem is that our problem also technically reduces to the problem that's used in the original result of Bravi, Gossett, and Koenig. So we also show that their problem is not in AC0 if you specifically care about their problem. Their problem is harder, has more structure. So we also just get a straightforward implication. All the implications go through everything about AC0 circuits of exponential size, et cetera. So that's basically all I wanted to say. I just wanted to give you an example, explanation of what the problem was and the story of how we came up with the problem. And it's totally intuitive. And these proofs are not super hard. Maybe the only hard part is the switching lemma, which in our paper is completely black box. So you can use the switching lemma as a black box. You don't have to actually understand how it's proved. Okay, that's all I wanted to say.
Thanks, Joey. Questions?
Does the separation still hold? You consider probabilistic classical circuits that should only compute the relation with bounded error?
Yes. So actually, every time I use a classical circuit class, you can put something like / randomized polynomial size advice. So as in they're allowed to start with a random polynomial sized probability distribution of their choice. That can be arbitrarily complicated. It could be even very hard to sample from for everything. Even the AC0 circuit. The AC0 circuit of exponential size can even start out with an exponentially complicated probability distribution. That's fine. So everything holds against this thing. So the way we phrase it in the paper actually is we phrase it as a distributional lower bound. So we give a hard input distribution. So then you can actually get rid of the probability in the AC0 circuit. So it does hold for that setting.
Question. How much? Sorry.
Sure.
How much are the results dependent on the choice of gate sets you pick in the classical and quantum case?
Okay, so in the classical setting, AC0 is extremely sensitive to the choice of gate sets. If you don't use AND and OR, if you use something else, and instead of AND and OR, you use, like, let's say, the parity gate or something, then this problem is actually very easily solvable because you would just compute the parity of X, and you would figure out which of the two cases you're in. So the complexity class AC0 is very sensitive to gate sets, and it is important that it's AND and OR. We also have a partial result here that we can extend all of this stuff, most of this stuff to AC0 with mod 2 gates, except we're only able to go to the point where we have a problem that needs a cat state. We're not able to get rid of the cat state like here. So this class is very sensitive to gate set. This one is not, doesn't matter. Any constant size gate set is fine. And for the quantum class, in some sense it is sensitive to the gate set because you need to be able to do these operations. Like the things I did over here, this is a controlled phase gate and this was a Hadamard, so you need these two gates. So if you have some gate set that cannot produce these two gates with a constant number of gates, then I mean, it might be that you might need log many gates if you use the Solovay-Kitaev theorem to do the decomposition, and then it won't be a constant depth circuit anymore. So it is somewhat sensitive to the gate set, but it's a very mild requirement. All you need is controlled phase and Hadamards.
So we take one more question. Ati, maybe you can go.
Yeah, I guess this is kind of reminiscent to the early days of quantum computing, like algorithms like Deutsch and Deutsch-Josephson and Bernstein-Vazirani, where the idea is to, like, no matter how contrived the problem is, like, can we just prove some separation? Do you see, is there any way to push this to some problem that would be not contrived, like kind of the Grover or Schwarz sort of the next step? Problem that's actually
Yeah. So I think the original work of Bravi, Gossett, and Koenig maybe is a little bit in that direction, except that problem is also somewhat contrived. Depends on your perspective. It's something like there's a matrix and it defines some quadratic form. You have to talk about its kernel over some field, and then you have to output some vector that's orthogonal to something because the kernel has a linear structure. That's also somewhat contrived, but you might say maybe that's more linear algebraic. But there is hope of going in that direction because that problem is somehow inherently about linear algebra, and there's hope that you could make it talk about like some regular problem that regular people know about rather than this very contrived problem. Our version, is just extremely contrived, I guess, in that sense. But that was actually part of the motivation for this work, and that's actually what makes this lower bound result go through as well, that our problem is input symmetric. We couldn't apply our techniques to their problem, or at least we failed at doing it because their problem has a lot of structure in the input, whereas here it doesn't matter, it's just all dependent on the Hamming weight, and this was key to making our lower bounds work.
Okay, so let's thank Robin again.